Okay, let's go ahead and look at the organic mechanism review. And what I want to do is look at eliminations, substitutions, and attack of ATP that we see in organic mechanisms. So what we're going to do is we're going to look at the first reaction where we have an E2 reaction. And what we're going to do is we're going to take a base, and remember that base inside an enzyme is one of the active site amino acids, the side chains, and we're going to deprotonate. And if you do some inventory, if you look at the reactant and the product, we are missing one of the hydrogens and we're missing one of the hydroxides. And so what we're going to do is we're going to take the base, deprotonate one of the protons, and the electrons will fall in to form the double bond. And what the leaving group will be is a hydroxide, but in organic mechanisms inside enzymes, there is always a proton available so that we have water coming off. And this is an E2 mechanism because we're going to see the dependence of both of those, the deprotonated proton and the leaving group, as part of the reaction. If we take a look at the second reaction, again, we're going to have an elimination, but this is an E1 intermediate. Okay, and so what happens in the E1 intermediate is the leaving group is the first to leave. We will rewrite the intermediate, and what we see on a carbon is a carbocation. Now that is high in energy, and this high energy state must be stabilized by the enzyme. The second movement in this will be a base, again, a side chain most likely, and it will deprotonate the proton and the elimination will occur and will lead to the product. Okay, so E1 and E2 is what happens first. Is it deprotonated first or is the leaving group leave first? Okay, the next series of events where we're going to take a look and we're going to attack the ATP, and we're going to do that by deprotonating the alcohol first. By deprotonating the alcohol, the electrons that were between the hydrogen and the oxygen are now negatively charged on the oxygen. The oxygen becomes a nucleophile. Now I can attack at either the alpha, the beta, or the gamma phosphate, and it's dependent upon what we see. And so what we're going to see is that we're going to have AMP attached. So that means we're going to have this part and this part and that part of the molecule attached to the hydroxide. Okay, and so what we're going to do is we're going to attack and make the connection. The electrons will kick up, the electrons will kick down. What falls off is PPI. And what we've connected is the RO to AMP. And so that would be an attack at an alpha. We see alpha attacks quite often. Most often what we see is this, where one phosphate is transferred. Very similarly, we're going to only transfer one phosphate. And so what the leaving group will be is a DP. The base will deprotonate. I will attack at the gamma. I will kick up. I will kick down. And this pair of electrons kicks onto that oxygen to be the ADP leaving group. The last things that we're going to take a look at is we're going to take a look at a substitution on this page. And we can see that we're going to have a nucleophile come in, and we're going to have a leaving group come off, and we're going to substitute. Now, an SN1, okay, means that the leaving group is the first thing that leaves. And so the leaving group that leaves first would be this. What we'll get is a carbocation. We'll have a hydrogen. We'll have a methyl group. And we'll have CH2, CH3. We'll also then react it with NH2, and I'll write it this way because we're only going to take off one. Now, in an organic flask, okay, the next step, I'm going to start off and do a few things. All right, I'll take this, and I can attack it here on this side, or I'm going to take a different color. I could attack it on this side. And what I'm going to be able to do in an organic flask is get two different intermediates. Okay, one could be this. Okay, H with the NH2, the CH2H3, and the methyl group. Or I'm going to have the H, the NH2, the CH3, and the ethylene group. What I get is a mixture of two different enantiomers. And the distribution would be 50-50%. This would be called a racemic mixture. Inside an enzyme, though, what we're going to do is we're going to retain only one of them. We will not get both. In an organic flask, you'll get both, a racemic mixture. In an enzyme, you're only going to get one, either the R or the S. Okay, in an SN2 attack, what we're going to see is the deprotonation, the attack, and the leaving group that come out. And what we're going to get is inversion of stereochemistry. Inversion of stereochemistry is very indicative of an SN2 attack. Okay, it is like an umbrella being attacked one and it pops open. That is a representation of an SN2 attack. Okay, those are the 6 kinds of reactions that I want you to be able to recognize: an E1, E2, an SN1, SN2, or where we attack the phosphate based upon what the outcome is. Did I transfer an AMP? Did I transfer a phosphate? Am I going to attack at the alpha or the beta, which are the two most often attacked places?